Let's look at OpenStack's College Physics Chapter 2, Problem 46. A swimmer bounces straight up from a diving board and falls feet first into a pool. She starts with a velocity of 4 meters per second, and her takeoff point is 1.8 meters above the pool. A. How long are her feet in the air? B. What is her highest point above the board? And C. What is her velocity when her feet hit the water? When we solve a problem like this, we have to be very organized, write down our knowns, unknowns, and draw a diagram. So I am actually going to start with a diagram because I'm going to be able to read a lot of things from it. So if that's the water level, and here is a diving board, and the diving board is 1.8 meters above the water, the trajectory of the diver will be something like this. She'll jump up with an initial velocity and go up. Gravity is going to pull her down, and then she's going to come back and hit the water. Now, I made this two-dimensional, even though it's only happening in the y direction, because it's easier for me to see this rather than overlapping the lines that I'm going to be drawing. So since everything is happening in the y direction only, I'm going to say that this is my y direction, and I'm going to make y be positive up. So everything that is moving up, like this initial velocity, is going to be positive. So this velocity is going to become smaller and smaller since acceleration of gravity acts on it. At the top here, the velocity is going to be 0 for a split second, and then change direction and start increasing. At this level, the velocity will be the same in magnitude but opposite in direction. So it will have that magnitude, but it will be down. And then the velocity is going to keep increasing until the diver hits the water, and her velocity is going to be negative and have a higher magnitude than the velocity over here. So let's draw some of these things. So I said this is my v initial. This is the v at the top, which is 0. And then down here, she'll have a larger velocity, v final in magnitude, and it's going to be opposite in direction. Now, let's look at the distances. So we know that the diver starts from some height y initial. She will go up to some maximum height, so I'm going to call this y max, and then turn around, fall down, and this will be her y final. This entire motion is governed by the acceleration of gravity, so I'm going to draw an arrow here down so that we remember that we have an acceleration of gravity acting on her throughout the motion. So let's write down our knowns and unknowns. We know a lot more things that the problem tells us, so I'm going to list all of those as well. So the diver, the swimmer starts with a velocity of 4 meters per second. So v initial is 4 meters per second. And she starts from an initial height of 1.8 meters. And I call that height y initial. So y initial is 1.80 meters. It seems that that's all we know in the problem, but we actually know more stuff. We know that at the maximum height, v at the top is 0. We know that the final height, y final, is 0. That's when she hits the water. And we also know that the acceleration throughout the motion is negative g, or negative 9.8 meters per second squared. So we know all of these quantities, even though the problem doesn't tell us, because we know the theory. So let's see what we're looking for. Our unknowns are the time that her feet are in the air. So I'm going to call that just t. That's a total time that she's in the air. B, we want to know her highest point above the board. So what the problem is saying is not that we want to know the highest point. We want the highest point above the board. So we only want y max minus y initial. We don't want the entire y max. So y max minus y initial is what we're looking for in part B. In part C, we want the velocity when her feet hit the water. So we want v final. All right, so let's see which equations we can use. I have my cheat sheet on the right here. And it's written in the x direction, but I'm going to replace the x's with y's because I'm working in the y direction. So I do not know the final velocity. That's the thing that we're solving for in part C. So I cannot use this equation to solve for time. The only other equation remaining is this one. So unfortunately, it's a quadratic equation, but let's see if we actually do have all the quantities we want. The final position we know is 0, is when the diver hits the water. We know the initial position is 1.8 meters. We know that the initial velocity is 4 meters per second. We're looking for time, and we know the acceleration is negative 9.8 meters per second squared. So we can use this equation. So let me rewrite it, and I'm going to write it in terms of y. So y, so this is part A. Y final is y initial plus v initial t plus 1/2 at squared. It's a quadratic equation. How about we write it out in the regular quadratic equation form? So I would have 1/2 a t squared plus v initial t plus y initial minus y final equals 0. So now I'm going to identify the coefficients. I know that this will be a. The coefficient of t squared is a. The coefficient of t is b. And this one is going to be c. And we have to remember the equation for the quadratic equation. So t, 1, 2, we're going to get two values for that, is negative b plus or minus square root b squared minus 4ac divided by 2a. So let's apply that to our problem. So we have t1, 2 is negative b. So that's negative v initial plus or minus square root of v initial quantity squared minus 4 times a, which is 1/2 a, times c, which is y initial minus y final. And we have to divide this by 2a, so that's 2 times 1/2 a. All right, let's plug in the numbers. I'm going to skip the units and the sig figs so that I can fit everything in this one line. So this is negative v initial, that's 4 meters per second, plus or minus square root of 4 squared minus 4 times 1/2 times a, which is negative 9.8. Close all my parentheses here. Times y initial, which is 1.8, minus y final, which is 0. So we have all of that on the top. And on the bottom, the 2 and the 1/2 give us a 1. So a is negative 9.8. All right, now if we plug these numbers into our calculator and solve for the time, we get two values. We get negative 0.323 seconds or positive 1.14 seconds. Since time moves forward, time should be a positive quantity. So here we have the correct time that we're looking for, the time that she was in the air. All right, now in part B, we're looking for y max minus y initial, and let's see which of the equations we can use. Well, the first one does not have any y's or x's, any distances in it, so we can't use that one. This one has x final, so that would be the maximum height. X initial is the initial height, so x final minus x initial is actually our y final minus y initial. We can use, this is what we're looking for. We know the initial velocity, we just solve for time, correct? And then we know the acceleration, so we can use this equation, right? Wrong. So we can't use this equation because the time here would be the time it takes for the diver to get from this point to the maximum height. That is not the time we solved for. We solved for the time that she was in the air this entire time. So we cannot use this equation because we don't know the time. Again, this time is the time from her initial position to the maximum height, and we don't know that time. So moving on to the next equation, we know that the final velocity at this maximum height is 0. We know that the initial velocity is 4 meters per second. We know the acceleration of gravity, so this is what we're looking for. So we can use this third equation. So let's write that down. So we have V final squared, and instead of final, I'm going to call it V final at the top squared, is equal to V initial squared plus 2a, and I'll call it delta y. It is this delta y that I'm looking for, so I'm going to solve for it. Delta y is V final top squared minus V initial squared divided by 2a. If we plug in the numbers, V top is 0 minus V initial, that is 4 squared, 4 meters per second squared, divided by 2 times negative 9.8 meters per second squared. And when we plug in the numbers, we get 0.816 meters. So now we know the height difference between her initial position and her maximum height. All right, now in part C, we're looking for her final velocity when she hits the water. Let's check again which of the equations would work. So V final is what we're looking for. V initial, we know it's 4 meters per second. We know the acceleration, and we know the total time that she was in the air. So she was in the air for a time t that we solved for in part A, so we know that. We can use that equation. So I'll rewrite it. V final equals V initial plus AT, and that would be 4 meters per second plus negative 9.8 meters per second squared times t, which was 1.14 seconds. And when I plug in the numbers, I get negative 7.17 meters per second. So let's check to see if this is actually correct. First of all, we get a negative number. Why do we get a negative number? Well, because the velocity is in the negative direction. Remember that we picked y to be positive going up. After the highest point here, her velocity is going to be negative, so that's indicated by the negative sign that we have here. So that's good. Now, the magnitude of the velocity is higher than what we started out with, and that also makes sense because starting from the diving board, her velocity is going to be decreasing. It's going to get 0 at the top for a split second, and then it's going to start increasing again in the negative direction. At the same level here, the magnitude of her velocity would be the same as the initial velocity, but it would be in the negative direction. So at this point, her velocity would be negative 4 meters per second. And then from here on, it still increases due to the acceleration and become larger than 4 in the negative direction. So that's what we have here. And one thing that we use throughout this, the solution of this problem, is we completely disregarded any sort of air resistance, drag, anything like that, which is why when I said that the velocity up here, the velocity at the initial point is equal in magnitude at with the velocity at this point, it was a correct statement disregarding air resistance or air drag.